Hi everyone. Today I'm going to be talking about joint work with my advisor Aaron Sidford on faster algorithms for maximum flow and the bipartite matching problem via a new energy maximization framework. So let's get started. In algorithm design, it's often important to use simpler or more structured subproblems inside of the main algorithm. In this vein, in the first half of the talk, I'm going to talk about recent advances in undirected flow problems. And then in the second half of the talk, I'm going to explain how to use these undirected flow problems to solve directed maximum flow via our new energy maximization framework. I'll start by introducing the max flow problem. Max flow problem is given a graph G with n vertices and m edges and capacitated edges. You want to send maximum flow from some source vertex S to a sink vertex T. So as an example, let's consider the following graph with the source and terminal marked, all the vertices and directed edges with capacities. A flow in the graph is just an assignment of real numbers to the edges. And we want to maximize the S to T flow. The flow has to satisfy some constraints. First, you can't violate any capacity constraints. Every edge, the amount of flow on it needs to be at most of the capacity. And also for every edge that's not the source of the sink, the incoming and outgoing flows must be equal. Finally, we want to maximize the total value of flow entering S, which is equal to the amount entering T. So this problem is very fundamental. There's been decades of important research on it. It encapsulates a lot of other problems, such as the min-SD cut, bipartite matching, scheduling problems. And there's small extensions of it, such as bin cost flow, optimal transport, and multi-commodity flow also. Solving this problem has been hard for both the more classical combinatorial methods, as well as the more recent continuous progress on the problem. Additionally, its improvements on this problem have often led to general techniques for various problems, such as some of the advances on approximate maximum flow leading to algorithms for approximate regression. In this sense, it's an excellent place to apply and develop new optimization techniques. As for what's known, following the early work of Karzanov and Tarjan, which showed that on unit graphs you can achieve an m to the 3/2 max flow time. This was improved to weighted graphs with a logarithmic dependence on weights by Goldberg and Rao. Madry in 2013, in a breakthrough result, broke through the m to the 3/2 barrier for unit weight graphs. Additionally, Lee Sidford has shown that you can get m root n instead of m root m. And in 2016, Madry improved the capacity dependence, though still polynomial. So our main result is an improved algorithm for unit weight max flow and bipartite matching, time m to the 11/8. To understand the exponent, Madry's algorithm is m to the 10/7, which is 3/2 minus 1/14. 11/8 is 3/2 minus 1/8, and 4/3 is 3/2 minus 1/6, which is a long desired runtime for exact max flow. And I'll get into a bit later why 4/3 is such a number. So again, our algorithm reduces the bipartite matching and min-SD cut in a u=1 case. To get towards how we prove our result, I'm going to talk about undirected flow problems. An undirected flow problem is, I have an undirected graph and I want to route one unit of flow from S to T, minimizing something. Natural things to minimize are some norms of the flow F. So if you want to minimize the infinity norm of the flow F, that actually corresponds to max flow. You can think of this as scaling the graph up and down, so that routing one unit from S to T while minimizing the largest capacity is equivalent to sending as much as I can from S to T while maintaining all capacities. Minimizing the one norm is just an ST shortest path, and a two norm corresponds to an electric flow or Laplacian system solving, which can be done in linear time by seminal results of Spielman and Tang. Um, Going back to the running times for the current progress on the max flow problem, the earliest work of Krasnov, Tandrin, Goldwyn, Grau used augmenting pads or some sort of shortest path potentials to run their algorithms. So in our view, this is like an L1 undirected primitive or an L1 primitive to help with the directed max flow problem. On the other hand, the more recent methods have been through interior point methods, which iterate on electric flows. Because L2 is closer to L infinity, it makes sense that these algorithms are better than the L1 versions. So it's natural to ask, can we actually go beyond electric flows? Can we go closer to L infinity? And our result, we think, gives like the first time where something past electric flows can actually be used to help max flow. A primitive that seems very interesting for max flow is, what if we had an epsilon approximate undirected max flow? Maybe that could just directly help with a directed max flow. And in a breakthrough result in 2011, CKMST showed an m to the 4/3 runtime for 1 minus epsilon approximate max flow. Their methods are based on using electric flows, but then changing edges depending on when the electric flow starts making less progress. And in the interior point methods of Madry do largely the same, and is why m to the 4/3 is such an interesting runtime to get for exact directed max flow. For undirected max flow, you can actually get linear time, m over epsilon, for 1 minus epsilon approximate. And here's how it works. You actually work more directly in the L infinity norm. What these results show is that you can build a coarse approximation, like an O of log, polylog approximation for the max flow, and then boost that using a gradient descent algorithm. So that's how you get a linear runtime. So in this sense, what if we just use like these L infinity primitives inside of interior point methods and get a faster max flow runtime? Unfortunately, it's not known how to do this. Somehow interior point methods naturally induce Hessians, which are quadratic forms. So these kind of inherently have L2. So what if we just use stronger things? It's known how to solve directed Laplacians also in linear time. And there's also been progress on p-norm flows. So when p gets large, it's closer to max flow. Unfortunately, none of the results on these problems, it was known how to apply these at all to directed max flow or speeding up these interior point methods for directed max flow. At this point, I'm going to talk about how we get our result, m to the 11/8 max flow, what the undirected flow problem we induce is, and what our energy maximization framework is. So at a high level, our algorithm does the following. First, we pre-process the graph in the following way. You can assume the graph is undirected. This is a known combinatorial reduction. Also, we can add some edges from S to T that help with the method we will run, but just additively impact the flow. So we can recover an exact max flow. Also, we're going to terminate our algorithm when the residual capacity is low, and then just run augmenting pads. Okay. We're going to wrap our method inside a general framework called an interior point method. What an interior point method does is we're going to iteratively route ST flow to improve our objective. Additionally, we're going to stay away from the capacity constraints as much as we can. And we're going to pick a potential, this log barrier function, to govern how we're going to add ST flow. Finally, while interior point methods do standard analysis get a root m iteration in 3 halves m to the 3 halves runtime bound, we need to figure out how to beat that. So here's what Madry's framework is for interior point methods. The algorithm maintains a feasible ST flow f of value v, and we're going to increase v throughout the algorithm. Additionally, on every edge, we're going to maintain forwards and backwards weights. The potential function we're going to track is the log barrier function. This log barrier function has the following components. We have the objective on f, which is f needs to route v units from S to t. Additionally, these log barriers ensure that the flow does not saturate the capacity constraints too much. Finally, the weights tell us how much we should care about each each log, how much we should care about every edge saturating its capacity constraints. Edge of the highway, we really don't want to saturate its capacity constraints. So how do we even move along this log barrier at all? As with standard interior point analysis, you can use the following types of steps. You can use a centering step, which says that if we're at an approximate minimizer for a fixed value of V, you can get to an exact minimizer in linear time just by routing some electric flows. The other thing we have to do is augment more flow. We have to increase the value of V to V plus delta while still getting close to a minimizer. And the way you do this is you compute an ST electric flow with resistances given by the Hessian of the log barrier and then add some multiple of that. Question is, how can we actually change the weights to ensure that the progress steps we're taking are larger than is governed by a naive analysis of interior point methods? To understand that, I guess first we're going to ask, what will cause the progress step to be small? Intuitively, the progress step is small when the electric flow we're trying to add has a lot of flow on some edges E that already have small residual capacity. Then we really can't add too much of it. To deal with this, following earlier ideas of CKMST, Madry 13, Madry 16, what they do is, well, when the electric flow is congested on an edge, if you increase the resistance of an edge, then you actually reduce the electric flow on it. So the way you increase resistance in the interior point framework is just by increasing the weights W plus and W minus on the edges. To analyze it, you track the electric flow energy as a potential function throughout the algorithm, and doing some trade-offs is how Madry 16 gets his algorithm. Now the question is, what is there to improve? How do we improve this at all? So our new approach is to do this thing called energy maximization to better understand how to do the weight changes in the algorithm. So in Madry 2016, he uses a combinatorial approach to do weight changes. He just computes edges that have large electric energy or electric flow and doubles the resistances to reduce it. On the other hand, we follow what we think is a more principled way. We define a new weight budgeted energy maximization problem. In other words, we're just going to ask, how can we increase the energy as much as possible under some weight budget? Which is somewhat what Madry is doing in his approach. We're going to solve this as its own optimization problem and use it to get the desired weight changes to take the electric flow step. So I'm going to define the energy maximization problem now. So here's the energy maximization problem. Let C be a cost of increasing the weights on the edge to increase the resistance by 1. Let W be the total budget we're willing to pay. And our goal is to maximize the energy increase possible for the electric flow with weight budget W. So written as an optimization problem looks like this. The max over, the objective is just C R prime 1 normalized W, where C is a diagonal cost matrix of the electric energy with resistances R plus R prime. Writing the electric energy as the min over all ST flows of the 2 norm, we can apply Simon's minimax theorem to flip the max and the min. Next, we just compute the inner max, and we get the following problem. An undirected flow problem out of the energy maximization framework. And the problem is, you want to minimize over ST flows of some 2 norm plus some infinity norm. So if we solve the energy maximization, if we solve the undirected flow problem, we can solve the energy maximization problem and then get good weight changes intuitively. But how do we solve this energy maximization problem? Well, if you exactly want to solve it, it's hard. If you set R equals 0, then it reduces to exact maximum flow, which that was what we were trying to solve in the first place. Fortunately, this is just to influence or guide our weight changes. So we only need some sort of approximate solution. So if we were able to get an approximate solution, we can get some approximately good weight changes, use them, take the electric flows, do some recentering operations, and then get a good algorithm. I actually want to emphasize here that a 1 plus epsilon approximation is not enough. We need something stronger. but I'll get into that on the next slide. So I'm going to talk about how to solve this. I'm going to define a new type of undirected flow problem for this talk called a smooth LP flow that was introduced by King, Penn, Sachideva, and Wang in 2019. What they proved is that when P is root log n, you can solve in almost linear time the following problem: min over ST flows of some 2 norm piece plus a P norm piece, which really has a lot of properties that we want. First of all, it's an undirected flow problem, much like our own. It has an electric flow part and also a high-powered P norm part that is unweighted, so only unit weights, but it is high-powered, which is very good. So now let's look at our energy maximization problem and the result of King, Penn, Sachideva, and Wang. If you notice several differences between the results, and I'm going to explain actually how to apply their result to solve our energy maximization problem. The first thing is that ours is infinity norm versus their P norm. Turns out that when P is root log n, it's actually an exact solve on their problem is enough to get good weight changes for us. Also, we had wanted some weight changes at the beginning, while this is just an undirected flow problem. Turns out you can do some sort of dual extraction tricks using the gradient because we got this using Sines Minimax theorem. Also, our result is the infinity norm squared versus their P norm to the P. But these are actually reducible via a binary search. Finally, the most tricky piece is that ours has a weight on the infinity norm piece, while their result is strictly for unweighted P norm pieces. So what we do is actually we just pick C equals the identity matrix and just hope that it works. And with a lot of faith, we're actually able to show that this is actually enough for our algorithm to work. So let me recap everything. So what our algorithm does is we're going to solve this mixed L2-LP flow problem, use it to compute weight changes. Then we're going to take an electric flow step and then do some manual recentering steps and then do standard recentering. And that's our complete algorithm. Finally, there's one little piece where we have to deal with the fact that we set the cost picture C identity and this induce some unnecessary weight changes, which we have to undo in the middle of the algorithm. And training everything up, you get an m to the 11/8 runtime. Additionally, our analysis does not have a potential function, like a global energy potential function like earlier results of Madry. I want to stress that our algorithm just solves this optimization problem, this mixed L2-LP flow, which gives us weights. We use those weights, take a step, and then we do this over and over, and that's just our whole algorithm. In this sense, well, also we can get an m to the 7/5 algorithm even without this unnatural weight reduction step. So m to the 7/5 still does improve over m to the 10/7. Okay. So as for where to go from here, the first question is, can we actually solve the LP flows for weighted graphs? While I don't have any direct applications of this, I think it would be very interesting and could easily open up new directions or approaches for either directed max flow for weighted graphs or directed max flow, even for unweighted graphs, just because these algorithms always introduce these like edge weights via the residual graph. Also, can we go beyond interior point methods and not use them as the outside framework that we run our algorithm in? Can we leave the L2 norm like approximate max flows do? And can we more directly use the smoothed L2-LP flows in our algorithm instead of using them to inform weight changes? Finally, can we use some sort of capacity scaling argument to get a logarithmic dependence on the capacity U instead of our polynomial dependence? So actually, we were recently able to give a new result in m to the 4/3 runtime for unit max flow and bipartite matching that makes progress towards, we think, several of these questions. So as for whether we can completely leave L2, we no longer use electric flows in our new algorithm. We define a new kind of flow called a divergence minimizing flow, which is the main like flow primitive we use to do our algorithm. Also, our new analysis more views the smooth L2LP flow as regularizing an electric flow and then solving that and taking the step. This regularization framework was also taken in the analysis of Axiotis, Madry, and Vladu, which using a result showed that you can do min cost flows in time m to the 4/3 plus little 1 log c, following or similar to how there was an m to the 10/7 min cost flow algorithm given Madry's in 2013's m to the 10/7 max flow algorithm. So that's my talk, and I would be happy to take questions over email or at the session later.